So we'll get rid of this part.
Okay. Okay. And we can go on screen. I think we can start it now. Kevin will be back shortly, I'm sure. So yes, there you are. Perfect. Okay, as long as you're ready, Kevin, let's go ahead and start it and let people in.
Okay, starting the webinar now.
Welcome to you early birds. We'll be getting started at the top of the hour. See you soon. Well, hello, everyone, and welcome to today's webinar on LED lighting and controls guidance for federal buildings. I'm Andrea Silvestri with GSA Center for Emerging Building Technologies in the Green Proving Ground. Before we get started, I'm going to run through just a few webinar logistics. So just first, a quick rundown of the agenda. First, we'll have a short introduction to the guide from Kevin Powell, the director of GSA's Center for Emerging Building Technologies. Then we'll hear from Michael Meyer from the Pacific Northwest National Laboratory, our subject matter expert and the author of the guide, who will give you a high-level overview of some of the guide's content. And at the end, we'll have Q&A. If we don't get through all of the questions at the end, we'll be following up as well. The webinar today is in listen-only mode, and you can submit questions by using the Q&A button on the bottom of your screen. And you don't need to wait until the end of the presentations to submit your questions. In fact, we encourage you to submit your questions well in advance of the Q&A session. Today's webinar is being recorded and will be shared with you all. You can find presentation slides and recordings for all past webinars on our webinar page at gsa.gov. And you can also access webinar recordings on our YouTube channel. The full guide is published on gsa.gov, and note that we have updated it with a few additions since we first published it in December. And now with that, I'd like to turn it over to Kevin Powell, the director of the Center for Emerging Building Technologies.
Thank you, Andrea, and welcome to all of our participants. We are really excited to release this guide. I guess next slide. But depending on a building's age and lighting system, lighting accounts for between 10 and 25% of a building's total electrical load. And the good news is that over the past decade, advances in LED technology have allowed us to achieve a 50% reduction in that electricity used for lighting over a fluorescent baseline. And then even better, advances in lighting control technology can save an additional 80% of that LED lighting energy. So recognizing these advances in September of 2022, Congress passed the Bulb Replacement Improving Government and High Efficiency Technology Act, which translates into something truly aptly named the BRIGHT Act. And the BRIGHT Act requires federal buildings to use the most energy efficient, life cycle cost-effective technology available today. And GSA has issued this guidance on how to best achieve that. GSA worked with Pacific Northwest National Lab and Michael Meyer, who I'll introduce in a second, to create practical guidance on how to select, design, and maintain the most effective lighting systems for federal facilities, incorporating lessons learned and best practices from 7 Green Proving Ground testbed evaluations at GSA. So I want to introduce Michael Meyer, who's really going to present all of this information to you. Michael Meyer has worked with the Pacific Northwest National Lab for the past 16 years. Michael has worked on multiple GSA projects focusing on lighting retrofits, envelope retrofits, and grid interactive efficient building projects or GEB projects. Michael not only supports GSA, but also works on appliance standards and energy codes for the Department of Energy. And when he's not doing all of that work, he is spending time with his teenage kids and his wife in Albany, New York. So, Michael, turning it over to you.
Thanks, Kevin. Thanks, GSA and everyone attending. So we're going to jump in. We have a lot to get through, and we look forward to the questions. The first thing you'll think about when you're doing a lighting project is, what is a light fixture? What are the light sources? This is the first set of things you'll consider is a retrofit. TLEDs, these are tubular LED. That's where the term TLED comes from. The idea is that there's 3 different options. Type A, these go directly in, replacing the fluorescent on the existing ballast. Then you have a type B, where you actually disconnect the wires to the ballast. You rerun that line voltage to the socket, and now you have that. Type C, you are going to still disconnect the wires to the ballast, but you have what's called a remote driver. The advantage there is you are able to operate multiple tubes from a single driver. It's also maybe probably easier to bring in some lighting controls directly with the external driver operation. A note of caution here, because you are now modifying this fixture in place, you should probably put, and actually it's required, a warning label on the type B and the type C. The idea is that the fluorescent ballast uses a different voltage, and by rewiring and getting rid of that ballast, you're now bringing in either 120 or 277 volts, and you can actually create some problems. A recent example I know of somebody accidentally replaced a type A TLED on a fixture that had already been replaced with rewired for type B, and it caused a pretty major electrical short and melted the end cap of the type A TLED. So in short, two things takes away. One, when you go to a type B or a type C, you're going to label your fixture that it's been rewired and modified, and there's a pretty standardized sticker that you can put on that available. And if you have done this, you're going to keep your type A and your type B away from each other, or don't relamp the same building with both type A and type B, just to prevent that potential confusion and prevent any future problems. These are pretty low first costs, and that's why they're often considered, but there's many other options, which we'll talk about in the next slide. So your next bigger options are a troffer retrofit kit, or there's other retrofit kits as well, but the most common two types of retrofits are either the troffer or the downlight. The troffer being the workhorse of most federal buildings and actually commercial buildings as well. These are the fixtures that are recessed in the ceiling. The kit's pretty easy. You pull out just the optical assembly of the existing fixture, disconnect a couple of the electrical components, the sockets and the ballast, boom, boom, boom. You have a retrofit kit in place. I've seen it done as little as 8-10 minutes. The advantage is it's a semi-new fixture, and you can have some controls, but then you always have the option of a new fixture. The advantage there is it's going to last longer because you're not retrofitting anything, as well as you can get that nicer appearance, maybe do it as part of a redesign or something along those lines. So that's what you do with a new fixture. Then there's also something called power over Ethernet. And the idea with power over Ethernet is you're eliminating the alternating current to direct current conversion, which has some inefficiencies built into it. So there's some savings there. You're also able to not have to run conduit into some places. Some states do require still running that cat cable in conduits. So in some cases, it's a material and labor advantage. But this does require a little more layout and planning to think through this. And obviously, because you're using power over Ethernet, your cybersecurity has to be at least addressed there as well. In terms of retrofit kits, if you are doing a retrofit, you're probably going to need to pull some type of electrical permit. The advantage there is you are not replacing above the ceiling, so you're not touching either the structural connections to the fixtures or the electrical, but depending on your jurisdiction, you may need to get an electrical permit to address that need. Next slide, please. The guide walks you through a number of different things. I'm only going to highlight them here just for the essence of time, but there's a huge deep dive on circadian lighting or the non-visual response. We can kind of give you some ideas what you consider. We're going to talk about color rendering and temperature in the next couple slides. We also discuss communication protocols. There's a number of ways to communicate with different types of fixtures and different control devices, as well as controls ready fixtures and interfaces. We do some discussions on dimming. And we also explain the difference between efficacy and the different factors into it, as well as all the different distribution types. And we'll show you flicker if you're not familiar with it. Hopefully you're not, because it's a less than sometimes desirable situation. And can you go into the next slide, please? So first, color temperature. Some of you may be familiar with this. If you're not, the idea is this is the appearance, the color appearance of the light source. There's a mathematical way we calculate it. We take the spectrum information. This value range really shows you what it looks like, where we have what's called warm white at 26 or 2500 Kelvin, and then it moves all the way up into what we call cool white at 6500 Kelvin. This is similar to what the sun does, and some manufacturers use those marketing terms. So like daylight and those type of things, they're similar type of concepts. You can see in the image below kind of what those color temperatures would look like in a space where you have the warm on the left and the cool on the right. Typically in the US, Most people prefer color temperatures in the 3,000 to 3,500 Kelvin range. And then there's some applications where you might want to consider a higher color temperature, but those tend to be more task specific, and you should always test that out. Next slide, please. Color rendering and fidelity. So the previous slide was about how color how it appears, how it looks to your eye. It doesn't actually tell you anything about how well it renders or it makes the objects in the space appear as their color. So there you're going to focus on either the term color rendering index, which is CRI, or the lighting industry in the last 7 years has moved over to what we call TM30, which is a more advanced metric. You can see here the two color swatches. So why we've moved to TM30 is because CRI is based on 8 basically pastel swatches. And while I like pastel when I'm coloring my Easter eggs, it's not representative of every object I see in life on a daily basis. TM30, 99 color samples, you can see it runs kind of the color gamut. So overall guidance is yes, you can still use CRI, and a CRI of 80 is pretty good for most interior applications, and a CRI of 70 is pretty good for most exterior applications. However, you can also use the TM30 metric, and there they get into what's called color fidelity, which is RF, and here the GSA guidance is recommending an 85 or better. The guide walks you through it all, but the key takeaway is there are new color metrics for color rendering, and you should consider them. And again, color rendering and color temperature, 2 different things. Next slide, please. So flicker. So this video is going to show you what flicker kind of experience is. It's essentially the change in time, the frequency. Sorry, I have to think about the correct technical definition of it. It's the fluctuation of the frequency of the electrical signal and the duty cycle. You can see it kind of flickering on the floor. There's actually about 3 different types of flicker. The phenomenon itself, it all depends on what the frequency rate is. There's different types of experiences of it. The LED industry is, sorry, I shouldn't say the LED industry. The lighting industry is working on flicker. This is something that was a problem when we introduced fluorescent technology in the early 80s, and they moved away from magnetic ballast to electronic ballast, and that's how they solved some of those problems. So some of that same research is being applied to LEDs. To reduce it, you're really going to be looking at higher frequency LED drivers. There's some other more subtlety to it. And the guide really walks you through everything you should think about, at least at a preliminary level. You could do advanced classes on flicker alone because of the way the perception works and those type of things. But the guide kind of walks you through to what to look for and the different waveforms to at least consider when you're trying to reduce flicker. Next slide, please. So I would say by far, one of the big things the guide does are these decision flow charts. So the first thing we're going to do is try to get you a sense of, well, how long are you planning to have this building? So if you're not going to have the building for a long period of time, and by building, we should also say the lighting system, you may consider a type A TLED. That's a kind of a short-term solution. And why it's a short-term solution is that fluorescent ballast that it operates on is going to fail at some point. It was installed probably 5, maybe 10 years ago. And the life of fluorescent ballast probably is only going to be 10 to 15 years. That's based on some other parts of the electrical components in that. So one of the challenges with a type A TLED is at some point, the fluorescent ballast will fail, and then you'll have to do something else. So you're probably thinking short term if you're considering a type A TLED, just if you're thinking about the life cycle cost scenario. If you're going to have the asset for 5 years, you might then be thinking about a type C TLED. And then if you're doing dimming, you may not need it, or if you don't need to do dimming, a type B TLED. If you're going to do a retrofit in the ceiling, if you're going to change some stuff, consider new fixtures. If you're not going to change the ceiling, retrofit kits are always a great option. Someone asked a question about if a retrofit kit and a new fixture both have electronic drivers and LED arrays, why would a new fixture have longer life? What I would suggest there is why the new fixture would have a slightly longer life is that the whole fixture is designed to accommodate for that body, for that LED system, through heat management and those type of things. In a retrofit kit, which I'm a big fan of, you're taking the existing fluorescent fixture, pulling out the optical assembly and the electrical guts, and then putting the LED array in. And you're still now dealing with how that shell manages heat. And so it's just not a one-for-one wholesale design of LEDs. So that's why I would say inherently your retrofit kit should have a slightly shorter life, not significantly, but when you design everything together as a wholesale idea, That's why I would expect the LED fixture to have a slightly longer life. Next slide. Energy controls. As Kevin mentioned, LEDs have done a lot. Lighting controls have also done a lot. So the idea here is your controls are required by energy code, and we'll talk about them in a second. But the first thing is that each control kind of does something different and has different savings potential. If your building is not using any controls right away, put a time clock in. It's the easiest thing you could do, just to turn off lights 24/7. But I'm hoping most of your buildings are already using some type of time clock. So then the next thing you should be thinking about is an aux sensor. These are devices that are going to turn off when the space is unoccupied. And you can also get vacancy control, which allows you to turn them on and off manually, and some other advantages. Depending on your occupant profile, these are 24, 25, even more savings. So it's a good thing to think about. Dimming, that would be also something you can consider. The idea is either you give personal control or in the space so people can set their own light levels. Again, you might see 15 to 20% savings there depending on the existing conditions in your space. Daylight controls are also a great idea to consider. This is going to reduce the electric light in the response to the amount of daylight. Now, of course, this is extremely dependent on your building location, the building design, and also a lot of things that are happening inside the space. And then there's always task tuning, where if you have one of these more advanced systems, you may realize that maybe you don't need as much light from the system, and you can use the network system to set that light level a little lower, and that's what's called task tuning. Next slide, please. The key thing to think about is that, as Kevin said, and this graph shows, depending on what your baseline scenario is, going from fluorescent or what we call the high intensity discharge, which is what's used in a lot of your industrial spaces, when you make that change to LED, you're getting about a 50% savings. That's pretty well known. There's some variables, but that's a pretty good estimate. Every control you add after that is really kind of against that next reduction. So while I said, hey, tuning, you might want to tune by 15 or 20%, when you factor it in against the LED baseline, you're really only seeing about a 10% savings against your original fluorescent baseline. And then you add in those occupancy sensors, and you add in your daylight sensing, you start running into some diminishing controls. So you really want to be selective and find the best control systems. It's not like, hey, let me keep adding everything in, because at some point you might run into some diminishing returns. But think about how your space works. Is there a lot of variable occupancy? Is there a lot of daylighting? Is there something else? And prioritize that for your control selection first, rather than just an all of the above approach. Be selective in your control strategies. Next slide, please. So then the document's going to spend a fair amount of time in designing a control system. While there's a lot to think about when you're considering fixtures and how they work, controls probably have more permutations and more complexity because of how you're going to communicate. And every time you make a choice, it affects something else that you have to think about. So we kind of came up with these 8 steps. First thing to think about is codes, whether or not then if you want to enhance capabilities, then you're going to talk about designing your zones, and we'll talk about what that means. System architecture obviously plays a role here, where your sensors are located and how they work, then control wiring, and then finally communication protocols. And then actually, once the building's operating, you probably should plan for retro and recommissioning, because in 4 years, you may need to redo it again and think about how the building's changed and retune those recommission those controls. Next slide, please. So, energy code. Everywhere in the United States has some form of an energy code. Federal buildings follow what's called ASHRAE Standard 90.1. There are some state deviations, though, depending on where you're located. At a high level, many of the codes work in the same idea, where for each space, you're going to have a series of controls that are required. This is a matrix that is a sample of what 90.1 looks like. You can see on the first column, each space, you have your small office, your medium office, and then your open plan office, anything that's over 300 square feet. And then you get into the different types of controls. So they're all going to require some type of local control, a switch on the wall, somewhere around, so I can either choose to turn the lights on or off. They're going to focus on how those lights turn on. Can they automatically turn on in the morning, or do you have to wait for someone to enter to turn the lights on and choose to turn them on for a little more additional savings? They're going to probably discuss whether or not there needs to be dimming, daylight response. So depending on your energy code, you're going to have this requirement. Different energy codes don't have it as a table. They have it as a list of spaces. It all depends. But at the end of the day, you're going to need to think about energy codes. And this is really the first step because it helps you figure out how your design is going to work. Next slide. Then after you've come up with a list of all the spaces you have and all the control requirements, that's your minimum. That's what code requires. Then you might want to think about enhanced capabilities. Lighting controls have gotten really smart, and thanks to computers and other things, we can do even more with them. We'll talk about HVAC and demand response in the next 2 slides, but 2 other things to consider. One would be what we call asset tracking or occupant tracking. And you can see from these heat maps, these were 2 simulations of a GSA building. And you can see where in the bottom one, through using the occupancy sensors, they were able to show where people opted to spend more of their day, because this was a hoteling space where they could choose where they worked throughout the day. This can help determine space utilization and say, well, wait a minute, everyone's over here. Do we need more people, more desks, those type of things. The top one, you can see how people move through the space. Also why that might be important. If you need information to be visible, you may choose that red pattern or red flow where people are walking the most to make sure that, hey, there's a bulletin that we want as many people's eyes to see on. That might be something. Also, controls have gotten so advanced now that we have 2-way bidirectional communication where we can do system diagnostics and energy reporting, where we can actually query how the fixture is behaving and get information about faults, as well as how much energy it's using. Next slide, please. So HVAC integration. So the idea of HVAC integration is you have spaces that are designed from a mechanical point of view, and they cool and they provide air and those type of things. But by using the occupancy information from the lighting system, we can actually help inform the mechanical system so that while we thought the building, often many of those offices were empty, occupied during the day, they may be unoccupied for an hour and a half while everyone's at a meeting. And if we had an occupancy sensor in that space, we could then send that information to the mechanical system and do what's called occupied standby. And the idea is you float back 1 or 2 degrees, and so you're providing either less heat or less cooling to that space, saving energy. But it's only 1 or 2 degrees. So when someone comes back into the office, it quickly ramps back up to the desired set point, making it more comfortable. We've seen about a 20% mechanical energy savings from this approach. It does require someone to actually think about how you communicate between the lighting system and the mechanical system. So it is not a quick, just out of the box. You do need to think through it, but it is very possible to do. It's also, there are energy codes that are also now looking at occupied setback. You don't have to do the energy code requirement. It doesn't say you have to do it through the lighting system. They're just encouraging you to look at that. Next slide, please. Demand response. So this is something place where lighting plays a great role. If you have a location where your demand charge is at least $5 or more, you should probably be thinking about a demand response program, and lighting is one of those examples. A GSA report did a pretty good analysis, and that was kind of their breakpoint. This works well in your large spaces, open offices, courtrooms, atria, lobbies, those type of things. The idea is as you can see on this graph on the right, on a hot day when the electrical grid is constrained, utilities need to shed load. That's called demand response. So they send a signal, you reduce the electric lighting in the space, saving power, reducing strain on the grid. Why is lighting so ideal? Lighting can dim, and LEDs are really easy to dim. Unlike fluorescent, which require a different ballast, which had a cost premium, almost every LED product out there rolling off the shelf right now is dimmable. At the driver level, you just have to bring a dimming signal to it. Second, your eye can not perceive a 20% reduction if it's done over 2 minutes. If it's done any longer, you really can't perceive it. But 2 minutes is about the threshold. So why? So I can dim my lighting almost immediately and shed load. Most of the other type of demand response methods, such as mechanical, it takes a little bit of time before the building can catch up from the thermal mass and those type of things. But so that's one reason why lighting is an ideal source. I can do it with a signal, I can shed load almost instantaneously. And again, most of the occupants in the space can't perceive those reductions. So we talked about because LEDs are efficient though, some people are considering other loads, but I would encourage you not to overlook it. You also have something to think about where you have an interaction where if you're using those daylight controls and you're already dimming, you may not have as much load to shed through demand response. So something to think about as you're considering your priorities. The other thing to consider is because you're bringing this ADR signal, you do need to just make sure you're dealing with the cyber mitigation and your IT security clearance, those type of things. Next slide. Determine your lighting zones. So in the lighting industry, the idea of a lighting zone is it's the group of lighting fixtures that are controlled together. So in this open plan office, you can see they have essentially 6 different lighting zones. You have a conference room and a couple other different places. Code's going to give you some high level guidance about that. For some spaces can only have a lighting zone of 600 square feet. Other spaces require no more than 10,000 square feet of control. So the code's going to give you very high level guidance on how big your zones can be. After that, you're then going to think about how many zones do I need? What fixtures do I want to control together? I see some person here asking about emergency lighting in the questions. So that might be something you might want to think about in your control zones of, do I need these set of fixtures to do both general lighting and emergency lighting? That might be a lighting zone you might want to put together. As you think about these zones, as I said, they're controlled together. So you might say, oh, well, these fixtures are going to be connected to this occupancy sensor. And these fixtures are going to be controlled by an occupancy sensor and a daylight sensor. So like in this example, maybe you have a lot of sun exposure in the bottom of this graph. And so in zone 3, you may have multiple types of controls, but in zone 1, you have a solid wall and no access to daylight. You may choose to only use an occupancy sensor in that type of zone. So that's what you're going to start thinking about when you do your zone controls of how many controls are going to be operating in these fixtures. And that helps you decide how big your each zone is going to be. One of the other challenges with zone design is how are you running the physical wires or connections to them? Some of these things can be done digitally through wireless controls and other means. Something to think about is luminaire level lighting controls, LLC. And the idea there is you're now putting a sensor, typically an aux sensor and probably a combined daylight sensor in each fixture. And then most often you're also going to do some networking capability, even if it's on site. And there you can actually have different types of control design zones, or you could change them after the fact digitally through an on-site tablet or even an iPhone or a mobile phone kind of application where you can rezone certain spaces through that. And that's an advantage of luminaire level lighting controls. Next slide, please. System architecture. I would be hard pressed to say there's any one type of architecture for any one type of building. Some spaces may have centrally networked where you have communication happening in all kinds of spaces. And then in 10% of the spaces, you may have standalone controls. It's okay to mix. That's the first thing I'm trying to get you to take away. But this tries to give you an idea of how you might think about this. So these 3 columns show you your different options. If you have a small space, standalone makes sense most of the time, but not all the time. So you might think about that. It gives you an idea. As you start layering in the number of control strategies you might have, again, that might tell you whether or not you want to have a standalone system versus a centrally networked system or a room-based system. If you're going to start doing demand response, again, that's going to tell you what some of your requirements are. Or if you're going to concerned about integration, those type of things. So a standalone control is really just a small little zone where you have a control device, a switch, an occupancy sensor, whatever, and they just communicate between the device and the fixture. A room-based control is kind of a small little brain somewhere on the wall, and it may give you a couple of what we call scenes, which are preset looks in the space. You can control some types of sensors with them, but you're limited to kind of what's coming into that box. Then you have the centrally networked, where you're going to have some type of communication between fixtures and some type of central device that allows you to do different things. Next slide, please. There are great questions coming in the question pane, so I just encourage people to keep asking about them. A person asking about fire alarms overriding the occupancy sensors in luminaire level lighting controls is a great question. And that's actually kind of leading into this slide, but I'll pause and think about that for a second. I don't know why you're asking about fire alarms overriding occupancy sensors. I think you might be alluding to emergency signals and needing to turn on the emergency lighting. And I think that might be the question. And there are ways to do that. I'm not an engineer though, so I can't explain that, but we'll follow up offline with that. Why luminaire level controls? The idea is that now I don't have to do as much thought process. I don't have to think about all my zones. I put a sensor in every fixture, and now I can actually do all that design after the fact. Once the building's up and operating, there are some advantages to that. Some of the energy codes, such as ASHRAE 90.1 is requiring occupancy sensors in open plan offices with zones no larger than 600 square feet. That kind of starts pushing you to this type of design, because now your zone size is so small, a luminaire level makes a lot more sense. Zone-based also has a great advantage in conference rooms and other types of spaces. So you really need to think about where these go. But I can't enough remind you that as you're thinking about this, to think about the IT side of it. Think about it early and think about how hard it is to do some of the remediation. Lighting systems are required to go through the GSA remediation process. Some have already gone through it, and there's a way they'll find out that information. But and also non-GSA stuff, I'm working on some Department of Defense. They also have this. So they're always concerned about just making sure information's not leaving the building through any means possible, or people coming in. So you really need to think about your IT mitigation. Next slide, please. So I've talked about it, and here it is, kind of a side-by-side comparison. So the image on the left is kind of a luminaire level lighting control. And you can see each blue dot is a sensor, and it's kind of on the side of the picture, versus the zone-based approach on the right. Again, many of the luminaire level products out there are combined daylight and occupancy sensors. And the advantage to this is you don't have to worry about it in the design phase as much. You can just now lay out put all the fixtures in the space. And then when you get into the space, you can say, yes, I want the first 2 rows to be connected to dim at this much rate from the daylight sensor, but the rows 3 and 4 to dim at a lower light level because they're not getting as much daylight. And maybe the 5th row, no daylight dimming because it's not getting any daylight. Whereas on the image on the right, you now really have to say, well, sensor 2 is controlling those 10 fixtures. So I have to make sure that that sensor coverage can do everything. And I have to think about kind of where are the weak points in that design layout, and make sure that sensor coverage is not falling in any gaps. So those are kind of the big takeaways between those two. You're going to have to commission the number of sensors you have. And again, we've gotten good at handheld tablets and phone ability to commission those fixtures, but it is still something you have to do. Whereas the one on the right, you have 5 sensors, and you still have to commission it, but it's going to hopefully be a little less because there are just fewer devices to control. Next slide, please. Configure wiring. So you're going to go through and figure out all the types of controls you have. Then you're going to talk about all the zoning that you might consider. And then finally, you're going to be thinking about, is it going to be wired, wireless, or a combination of the two? And you may actually talk about this as an iterative process. You may decide early on if it needs to be wired, that's going to affect certain choices. If not, you're going to think through all those things. One thing to think about with wireless communication devices, depending on how they work, if they're standalone, they may have battery power has to be a thing to think about. And you may have a limited life, 10 years of that battery device or less. So you need to think about your whole life cycle cost as you start thinking of wired versus wireless. In terms of this table provides a pretty quick overview. In terms of wired, if you're doing a new construction, wired can make a lot of sense. If you're doing wireless, You may want to do wireless in a new construction for ease of future planning. And if you're going to move walls and move rooms, you can do a lot of standalone controls with wired fixtures. It's a little harder to do wireless with standalone controls. There are some options, but it starts getting complicated. Cost is where you're going to start really considering the two options. You're probably going to spend more money and time in wired solutions. So that's one thing trade-off. The advantage with wireless is it's wireless. You don't have to run all the communication wires, but your IT mitigation may be a little longer because again, there's more wireless protocols that have to be managed than in a possible wired situation. Wired probably still does require possibly some IT mitigation if you're using a network system. So you can't just say, hey, I don't have to worry about that. And in both scenario, you could probably integrate with a building automation system. Next slide, please. So then we also want to just discuss kind of a discussion about communication protocols. So the lighting industry in the US and North America has primarily used, when it came to fluorescent technology, what's called analog, also known as 0 to 10 volt. In contrast, in Europe, they have leaned more into digital and this DALI 2 protocol. We are starting to see in the last 4 or 5 years, more DALI 2 products come available in North America. So key takeaways between these two is the data exchange. 0 to 10 is analog and it's one way. So it can only send information out. It can't query it. And because it's analog, it's a very low signal and doesn't have a lot of information. Digital is sending actually information in that signal. So it can actually get information back from in the two-way communication. So there's one thing different there. Luminaire addressability, you're going to get that more in your DALI 2 system. It is harder to get in a 0 to 10 system. You have to do a lot more complications with controllers and those type of things. Your wiring is going to play a role in 0 to 10, whereas with a digital system, I can go in and reconfigure those type of things. Dimming precision is different between the two of those. Many people inherently think that 0 to 10 has no cybersecurity risk. At the end of the day, the 0 to 10 is really what's just communicating with the LED diodes. You might have other communication systems out there in your building that have to be mitigated with the lighting system. So don't think just because it's 0 to 10, there is no cyber mitigation. You might have other communication modules that do communicate other protocols that do need to be mitigated. DALI 2 does require a little cyber mitigation, but it's pretty straightforward. Availability, as I mentioned, 0 to 10 is pretty widely available in the United States, but there are different protocols, so you need to think through it. There are more manufacturers who are beginning to have DALI 2 products available, so it's changing over time. Next slide, please. So along the way, we received some questions about DALI 1 versus DALI 2. So as I mentioned, there was a lot of less uptake on DALI in North America. Primarily, that was DALI 1. Here's just a quick comparison between DALI 1 and DALI 2. So DALI 1 was basically sunset in the mid-teens, and then they shifted over to the DALI 2. And you can see these quick comparisons. DALI 1 really only focused on the driver, and then you could have proprietary communication devices elsewhere in the system, and that's where the technology ran into some pushback. DALI 2, they're going to test the whole thing. They're going to make sure that the products communicate, and it's not just the driver. They're going to actually make sure the other devices can communicate with it. And so you're reducing some of those problems they had with DALI 1. Testing, that's a key component in DALI 2. They're going to actually make sure that the widgets communicate with each other, similar to how BACnet works, where they actually make sure the BACnet devices communicate. It's not just, oh, it works. They actually do a little on-site testing, or actually they do some testing there. Next slide, please. So you've built your building. Plan for it to live 20, 50 years. Think about retro and recommissioning. So first thing you should do is, let's make sure we stop here. Commission your lighting control system. Commission your lighting system. So you've gone through the retrofit process. You've gone through the new building process. Make sure your controls and everything is working the way as they were intended to work. That's the baseline commissioning. Then the people come in the space and the building's operating. Then things change. Spaces change. occupancy patterns change. I think the pandemic's a great example. You know, pre-2020, everyone was in there from 8 to 5. Now you have a much more flexible workspace. That may affect how your occupancy sensors work. That may affect other control systems. Don't just assume nothing changed. Plan for 4 or 5 years later to just do some cursory retro commissioning. Think about a maintenance schedule. It's not just about how your controls are working. How are you getting firmware updates to your devices? As devices get smarter, they also need to get updated. So they're making sure that either security lapses or other failure points are being addressed, as well as new features get evaluated. So you add that to it. Don't just think that once I have my lighting control system working, I don't have to ever come back to it. We don't do that with mechanical. We definitely do a lot of routine maintenance on our mechanical systems. We should factor in a little routine maintenance in our lighting systems to get the most out of them. Next slide, please. So we kind of gave you those 7, 8 steps. Then we also have this flow chart. So the idea here is to help you think about when you might want to consider the different types of lighting controls. You have the standalone, you have the room-based, and then you have the centrally networked. Is your space for more than 5 people? No? Well, all right, well, maybe a standalone makes sense then. Again, these are intended they work well in small spaces, and we picked 5 because that's kind of a dividing point. There's no hard science in this number, but the idea is how many people are in your space? Is it a small space? Oh, okay, well, standalone might make sense. Are you going to communicate with your mechanical system? Well, that pushes you already into certain choices that you start needing to make early on. So that's where you're going to go that way. You might consider a room-based system. And again, you can do that with certain communication systems. Do you need many sensors in the space? Well, if you need many sensors in the space, you're probably still moving to that centralized network control system because of the complexities and the ease of being able to modify things and commission things from a central point of view. If you don't have a lot of sensor in the space, well, maybe you're back to a zone-based system. So the idea is trying to walk you through to consider how this works, rather than just saying, here's all this information, now you make the best choice. We're trying to give you a flow chart to help you think. Your building will vary, I promise you, but it's meant to make you think through the process. Next slide, please. Finally, as Kevin mentioned, the Bright Act is really looking at life cycle cost effectiveness. TLEDs are a very, very efficient first choice cost, and I totally get why people consider those. But as I mentioned early on, that type A TLED, those ballasts are going to fail. They have to be managed later on, and that's a life cycle cost thing that you need to think about. So we put together some scenarios looking at a 15-year life cycle of different scenarios, and we give you different savings amounts, different energy savings, and then what the actual cost would be based on a number of factors. And you got to kind of see a different range of simple payback and overall 15-year life cycle. The idea is trying to help you think it through, well, what's happening in my building and what is the best choice, rather than either the first cost, the simple payback, but really get you to that life cycle cost. Think about it as the holistic approach. Overall, retrofit kit with zone-based control can be a pretty efficient, good choice. So it's not something to slough at. Really consider it. If you want the maximum amount of savings and for the best amount of use of your money, you're probably looking at a network control system that you're also connecting to the mechanical system, because you're getting that additional savings from reducing the mechanical energy, which is often more energy than the lighting system's using. So if you can curb some of that mechanical energy, it's kind of extra savings, and it helps make that network system more cost effective than just doing a network system by itself. But we provide a bunch of scenarios in the guide. And also the thing to think about is that fluorescent lamps have been started to be banned by certain states. So you can't sell them anymore because of the mercury content starting in 24, 25, and 26, depending where you are. Your fluorescent tubes are going away. You're going to need to be thinking of other options, and we're just trying to give you a sense of how to figure that out. Next slide, please. There's been a number of questions throughout this. I appreciate it, and I think we're going to try to address some of them.
We are great. Thank you, Michael. So we'll jump right in. Is the guide applicable to commercial and industrial facilities as well?
Commercial, yes. Most of the federal portfolio is relatively a commercial space, other than I would say the VA, which is heavily more on the medical side. Industrial less so, mainly because we didn't get into high intensity discharge sources, which is in many industrial spaces, and some of the other challenges with it. So at a high level, I would say yes to commercial spaces. There's some good things in there about industrial, but less applicable to industrial.
Great. A couple of POE questions. So how does POE improve efficiency when the AC-DC conversion moves from the fixture to the switch?
Okay, the POE is a little more complex than a normal thing. So the idea here is that if, let's say we have 10 fixtures in this space, each fixture is doing an AC to DC conversion, because at the end of the day, LEDs are a DC device. So we have 10 conversions. If I have a switch and then we run 10 Cat6 cables to those 10 fixtures, then I'm only running one DC conversion at the switch, and I'm then connecting to the PoE drivers in the fixtures. So that would be where you're seeing some efficiency changes. Full disclosure, PoE systems are nuanced, and the savings I have seen in both some situations where there are savings, and as one of my colleagues said, well, we don't know on this one, we think it actually may be a slight increase. So there are many benefits of PoE to consider, but it is not a slam dunk savings in some cases.
Great, thank you. Is there anything on the horizon to standardize across the industry the fixtures and pigtail attachments so that the retrofit kits can be installed quickly by simply unplugging the old and plugging in the new? The wide variety of ballasts in existing fixtures has caused us to slow down the lighting retrofit since there are so many compatibility issues.
That's a great question. In terms of if it's an already existing fixture, I don't understand how they would have what's already in space. So I don't think that would answer that person's question. And so you're always left with what's in the space. So you can't really retrofit anything. You can't standardize there. The lighting industry, I think, is a great example. You know, the light socket. There's many places where the lighting industry has standardized. Ballast quick disconnect is also another example where the lighting industry has found ways to standardize as well. I would encourage you also to reach out to the manufacturers you work with and voice where certain things are that are needed for standardization. Some things are ubiquitous enough that there's no competitive or technical advantage for a differentiation. Other times there are reasons for it. But in terms of mechanical electrical connections, standardization often makes more sense. And again, I always go back to the light socket. We standardize once, there's reasons to standardize other places.
What about delamping? Is that a reasonable solution, and are there guides on how to accomplish it?
So delamping, and if you're delamping, I'm assuming you're using a fluorescent fixture. So the idea is you have a fluorescent space, or you have space where you have a 3-lamp, maybe a 4-lamp, possibly a 2-lamp fixture, or you have so many fixtures in there, I can take out the lamps of every other fixture. Those are your ideas on delamping. It saves some energy in just that you're using less because you don't have a tube in that socket. During the early 2000 California energy crisis, because of the way the utilities were working, delamping was a very common strategy. I would be caution against it because the savings are not, from what I understand, is the ballast is optimized to operate so many lamps. And while you're operating fewer lamps, it's not at its optimization point. So it's not a straight savings is what I'm trying to say. So that's it. I would encourage you less at this point, again, because many fluorescent products are going away through either voluntary manufacturer retirement because they're switching to LED, or because of, as I said, a few states have banned the mercury content. Long term, you should probably be avoiding. I would just encourage you to look beyond delamping for other solutions.
Does the 50% fluorescent to LED savings cited exclude any savings that might be realized by the reduced load on the HVAC system?
Yeah, the 50% savings, it's a pretty general number. Again, there's a lot of nuance. I would sometimes have said between 40 and 60. The idea is that LEDs are more efficient than LED at the source level. Then you don't have any, you don't have certain optical issues, and then often there's some distribution and light level changes as well. So that's where if I can pull a case study here, I can pull a case study here. 50%, it's a pretty good number. Yes, then in your cooling dominated buildings, let's come back to that. Cooling dominated buildings, you would probably have some residual. You'd have some residual savings from the reduced electrical load. In heating dominated buildings, you actually probably would increase some of your energy load a little bit because you are not producing the heat from the lighting system anymore, and therefore your heating system might need to actually uptake a little bit. But I think that's in the noise.
Great. Another POE question. Do the voltage drop requirements of ASHRAE 90.1 apply to POE?
Oh, okay. All right, so voltage requirements are in section 8 of 90.1, and they're really more applying to the larger electrical system. That all being said, I don't know. We'll follow up. I also help support 90.1. No one's ever brought that up as a question or an issue, so I don't have a better answer, but good question though.
Great. On dimming, are you talking about 20% of the electrical load or of illuminance?
So also a good question. I've said dimming many times through this presentation and in different contexts. So let's be specific. In terms of visual perception, you can dim the light output by 20%, and there's a negligible to no visual perception change at the eye. That there's data on that I can point you to. LEDs have a very, at least at the high level, have a very close one-to-one relationship between output and power, unlike fluorescent where it was more of a curve. So ideally, if you're dimming your LED by 10%, you should have a 10% light output as well, reduction as well. So I hope I answered that person's question, but I'll leave it at that.
Great. Do you think for demand response, you can couple zone lighting control with task lighting for more granular control?
So in a zone-based system, I have 8 fixtures that are somehow controlled by one control point, and then you're bringing in demand response. So ideally, you have some means of telling those fixtures to dim, because that's what you need in demand response. You could, I guess what this person may be asking, offset some of the reduction in lighting with task lighting, and just as long, I would hope that you're not increasing your plug load that reduces your demand savings. That's a little more complex. I think it requires a layout.
Yeah, sounds good. Does the LCC cost calculation include the different warranty and deferred maintenance expenses? A TLED warranty of 5 years versus kits at 10 years.
Also a good question. No, it does not get into warranty in that we assume that the systems would last as long as roughly kind of some of those guidance, but we didn't get into whether or not there would be warranty. What was the other question there, Andrea?
I think that was a deferred maintenance expense.
No, we did not get into deferred maintenance. We assumed that for a TLED, you'd have to replace it after so many cycles. Yeah, we did not get into deferred maintenance.
What's the impact of the harmonics from the LED power supplies to noise sensitive systems such as communications training facilities or instrument landing systems training?
I'm not an electrical engineer. In terms of instrument landing systems, I believe there are LEDs used in lots of airport and other facilities like that. I have not heard of huge carve-outs related to that. I know there was a lot of concern in the early days of the introduction of LEDs, but I've not heard that harmonics have been a long-term concern with the LED. And we can follow up there a little more. No one has advised me avoid LEDs in these spaces for harmonics. I know that on some ships and near nuclear power sources and other stuff, they had early failures because of the electronics, and so they still use fluorescence in some places, but I don't believe that's a harmonics issue.
Class P fluorescent ballasts had internal thermal protection and it was a good practice. Should inline fuses or external thermal protection be installed for LED lights?
Again, I'm not an electrical engineer on that one, and I don't know why we installed them for fluorescent ballasts. So we can follow up on that one. Again, no one has there's many millions of LEDs out in the world, and I've not heard anyone advocate for inline fuses with LEDs. So it's a question of why did we have it with Class P, as this person asking, and not LED. So, but of all the continuing education and trade magazines I've ever read, no, I've not seen this pop up as a concern. So we'll follow up, but at the moment, I'm relying on no one's raised it yet.
I found that the lumen output is a lot more for LED than fluorescent. Should you do a study before the retrofit?
Great question. First, lumens for everybody on the call is the basic amount of light emitted. It's equivalent of a gallon kind of idea. You should do a study. I'm not going to say that the lumen output is more, because there are tons of products out there where I can say, well, this lumen output is less, and it'll show on their package. So there's that. Lumen is a very broad metric, and it's just how much light. It does not tell you where the light's going. It doesn't tell you how much light, and it could be more intense and those type of things, and that matters. So you should you should get some type of estimate of how much light you have in your space and how much you're retrofitting it with. You should know that fluorescents degrade very little, roughly about 5 to 8% over their life. LEDs are going to have a little more, but a longer degradation, meaning that a fluorescent tube is going to last, let's say 10 years, depending on your operating cycle, and only degrade about 8%, whereas fluorescents can easily last more than 10, 20 years, and they're just going to have a slower degradation. So you have to think about that in your calculations. The other things to think about is brightness / glare, in that fluorescent tubes are very omnidirectional. And while there is still some potential for some glare for some fluorescent fixture, the nature of LEDs being so much smaller, there's greater potential just from an optical design from LEDs. So some people misconstrue glare as light output, and you should first try to have low glare fixtures. And that it's something you should strive for, but that's different than light output. So I'm just trying to say, you should consider the GSA guide references some of the IES, the Illuminated Engineering Society, where we're going to provide you guidance on how much light you should have in your space. You should do analysis how much light you need, but don't misconstrue glare and brightness for light output.
I think this is a follow-up question. So how would photometrics be done with an LED tube, type A or B tubes in a retrofitting? How would you do the study in a fluorescent fixture?
Okay, so we have some data on this. The quick answer is you're going to have a lumen output on the fluorescent tube, and you're going to have a lumen output on the TLED. An early Department of Energy caliper report, circa 2012, found about a 10% increase in light output from the TLED compared to a fluorescent tube, because what's happening is you're losing some internal reflection. So what I'm trying to say here is if I have a fluorescent tube that's producing 2,500 lumens, and I have a TLED that's producing, let's say, 1,800 lumens, in that same fixture, the early data said you would actually get about 10% more light out from the TLED because of all the internal losses from the fluorescent system. So I can actually say, well, wait a minute, that's close to a near equivalent. The other thing I would tell you in a photometric analysis that you should consider is close. We're talking ballpark close. You don't need, if your fluorescent system is giving you 35-foot candles, and you don't need to come in at 35. You can come in at 33, can come in at 37. So there's definitely room for that. Same with lumens. If your fluorescent system, if your lamp is producing 2,500 lumens, 2200 lumens is good. 2800 lumens is good. There's a lot of art to lighting design, and these numbers are not, you do not have to meet these numbers exact. They're broad.
Okay, great. This is our last question. I know we're at time, so we'll wrap up. Do we have to worry about power quality due to LED?
Again, all the research that I've seen and not seen people raise is that total harmonics and power factor for electronic drivers is good, and power quality does not seem to be an issue that is being raised for LEDs.
Great. Thank you, Michael. Thanks so much for your presentation. And thanks for all these great questions. And we'll be following up with Q&A, as well as sending out the slides and the recording. And this is eligible for continuing education credit, both with the American Institute of Architects and for GSA attendees, a continuous learning point. So to receive that credit, you'll be receiving a post-webinar survey. Complete that and we can send you credit. Thank you, Kevin and Michael, and thanks everyone for joining us today. We really appreciate your time.